Good morning, everyone. My name is John Micco. I'm here from VMware to give this talk about CI and CD, what I've been working on for the last more than 20 years of my life. I started out working in CI/CD at MathWorks, which makes MATLAB and Simulink. You may have heard of them. I then went to Google. I was at Google for about 7 years doing CI and CD work there. And now I'm at VMware. I'm working to sort of bring all of the teams at VMware into modern CI, CD practices and automation. So I want to talk a little bit about sort of how testing automation is done. I want to thank very much the AST committee for inviting me here to speak to you today. And hopefully you'll have some questions. We can talk about those kind of at the end. So without further ado, let's get started. So I don't know, it's pretty simple. People think it's pretty simple. The industry standard for automated software testing is what? Continuous integration. And you run the tests after every commit, it's sort of after developers make changes. And the expected outcome is that the tests pass. Pretty simple, right? You want the developers to make a change. You want it to pass the tests. And you want failure to mean that broken code was committed or something is wrong with the software, right? And it's really only as good as your automated testing inventory. If you don't have tests that cover certain features of your product, you're not going to be able to find those in continuous integration. They'll slip through and maybe get caught by customers, hopefully not, but that can happen, right? So that's kind of the very basic, that's what continuous integration is, right? So what are the goals of continuous integration? Why do we do it? We do it to sort of minimize the customer facing defects. That's the thing, that's a property. You don't want very many defects to go to your customers. You want to maximize the release frequency because the more often you ship code to customers, the more they're getting value out of the work that your engineers and your developers are doing, right? Also, if you ship in smaller increments, it's easier to find and to fix problems, and problems tend to be smaller. You want to detect defects with the software systems as soon as you can, right? Because the longer it takes to find the problem, the more it costs to fix it. Every study in our industry has shown that the longer it takes to find a software defect, the more it costs the organization to fix it, right? So you want to minimize the human costs associated with testing, the toil, the things that developers and QE engineers have to do. And you want to minimize the machine costs associated with testing, right? When we were at Google, we kind of figured out that if we ran every test that we had 6.5 million tests. If we ran them all, every time a developer made a change, which happened several times a second, we would have used more computers than Google search used. So at some point, it doesn't become cost effective to throw all those tests at every single change, right? It just doesn't make sense. And so software testing is really about managing risk and finding appropriate trade-offs, right? There's no way to sort of guarantee that there aren't going to be any problems. At the end of the day, it's only as good as your testing inventory. It's only as good as how many computers you have. And zero defects is kind of a fallacy. No, even simple software system is defect free. That's just not something that really happens. Right. So here's some statistics that are interesting, right, about how this works, right? So at Google, almost 92% of the changes don't have a test failure that could be caught by a test that you have. This means for most changes, 92% at Google, you could just skip all the testing and you wouldn't miss a defect because the developer didn't submit one, right? Only 8% of the changes were interesting in that they had a failure that could be detected by running a test, right? And across Google and Netflix and VMware, 60 to 80% of transitions from pass, the test was passing, pass, all of a sudden it fails, right? 60 to 80% of those first transitions are flakes. Flake, what's a flake? A flake is when the test fails and passes with the same software version. So you have a version of your software that you've built, you're testing it, you run a test, it passes, you run the same test, it fails, that's a flaky result, right? So the best practice, most companies are doing this, Google does this, Facebook does it, Netflix, VMware, you retry failing tests. At VMware, if you retry tests twice, you reduce the failure volume by 92%. So you have these failures occurring, and about 92% of them are actually just flaky. Now, you do want to keep track of flakiness. You want to reduce it. You want to drive it down. We'll talk about that in a minute in more detail. But that's kind of a stunning statistic that most often these tests that are designed to catch real failures are catching test flakiness. And that flakiness may or may not have been caused by any recent submission. It could have been in there in the software from the very beginning or in the test from the very beginning. So given that this is a really sparse search space, right? I mean, 92% of changes won't have a detectable problem, right? So only 8% do. And of those, many of that, there's a lot of noise in the system with these flaky results, right? So it's really hard to train models for regression test selection. Some of the early efforts that we worked on to do this were fraught with peril. Like we made one that said, okay, let's look at the history of a test, pass and fail, and tests that transition more or that have pass and fail results more, we'll prioritize those. And what we essentially ended up doing was prioritizing tests that were highly flaky, which didn't really give us any good signal about catching real problems, which is really the goal of CI testing. You want to catch the real problems. You want to kind of ignore the flakiness, which is kind of hard to do given the prevalence of it. So it's hard to train these models and to verify them to make sure they're correct. So even when machine resources are flexible, you need to limit your resource consumption. As I said, at Google, we would have been using more machines than Google search was using. It would have been highly unlikely or too expensive, prohibitively expensive to just throw all those computers at the problem and say, okay, we're just going to run those 6.5 million tests every single time, right? You need to optimize the use of resources that you have available for testing. You really want to squeeze every last drop out of all of the machines that you're willing to spend on testing, which means you want to saturate your pool of machines. You want to constantly be having all the machines be busy running the most valuable tests that can help reduce the risk of latent defects. You also need queuing because at some points you're going to overconsume your capacity and you don't want just an error message to come out because that introduces more noise into the system. What you want is for those tests to just wait until the machine resources are available. So you really have to improve your test scheduling. This is super important, right? You want to retries to be put in place for test flakiness because that just eliminates a lot of human manual toil investigating problems that aren't really problems. You want to monitor your flakiness rates. You want to understand how flaky tests are, and you want to fix them if you can. You want to reserve capacity in your system for things like regression ID. So I'll explain this in a minute, but if you have a test that was passing and now it's failing and there's a set of changes that came in between, you want to be able to do bisection and figure out, okay, which of those changes broke the test. So we're going to reserve some capacity for doing things like that. And generally, interactive runs from a developer, like a pre-submit testing or manual testing, they should have higher priority than the CI system has, because you want to encourage developers to write and to execute tests and to make sure to qualify their submissions as best they can before they commit them, to reduce the risk that they're actually going to commit a defect. They're going to check something in that breaks, right? That's what you want to do. So automation should use 100% of the capacity to reduce the risk of defects. And the scheduling should be based on when the utilization of that machine capacity that you've reserved for testing, when the utilization drops, that's when you want to schedule more runs, and you want to do it as frequently as you sort of can, right? You want to monitor for CPU and memory footprint, bin packing. You should strive for 100% usage of every last bit of the compute hardware that you have. At Google, our testing farm was the most consistently loaded set of machines at Google. That means that we were using consistently our machine capacity more so than search, more so than any of the other feature functions that Google had, because we had really good algorithms for packing the testing and the building into these machines and keeping them saturated in terms of CPU, memory usage, whatever it was completely saturated at all times. So you continuously want to push on removing and reducing the overhead, right? How long it takes to set up a test, how long it takes to tear down the test. You want to reduce these things to the minimum possible. And you also want to reuse the test setups when you can. I mean, sometimes you end up with statefulness. You can't reuse a test setup because the state has been corrupted in some way, and maybe you want to start with a clean state. Excuse me. But reusing them is definitely important to help optimize the system, right? So that's kind of how it works. So regression test selection, what does this mean? It means basically you want to have a good way of picking the tests that are going to break, right? And there's lots of techniques out there for reducing the set of tests that you're going to run. Test prioritization techniques, regression test selection, which is this thing, sampling, all kinds of things that you can do, AI, all kinds of things that you can do to decide which tests. Now, a perfect regression test selection system could skip 99.2% of all test runs and not miss a transition. This is a statistic from Google, right? So basically what that means is since there's only 8% of the submissions that have a detectable problem at all, right? So that reduces the space to 8%, right? And then of those 8% that had a detectable transition, of the 6.5 million tests, maybe only 5 of them failed, right? So you have a very small space of tests that you need to execute to find every problem. If you're omniscient and you knew ahead of time that this test was going to break, this test 5 was going to break on submission 3, right? You would only run test 5 on submission 3, and you wouldn't run any of the other tests that you have because they're not going to transition on that one. So the best regression test selection, the ideal one, would be skip all of the tests except the ones that are going to break, right? And you'd have to know that ahead of time. Don't ask me how you'd know that, but that would be the best outcome that you could get. You could spend a fraction of the resources that you're now spending. By about 99.2%, you could reduce the amount of capacity and machines that you could have. If someone can figure out how to do that, please let me know. I'm open to that idea, right? So it's a good application area for AI, but you have to be very careful. I've seen a lot of proposals for how to use AI in this space that really don't take into account that the search space is so sparse. And they say, look, we skipped lots of tests and we didn't miss any transitions. So our AI must be great. Well, no, you really need to measure the RTS algorithms. And I'll show you how we did that. We did a study about that at Google for precision and recall. You want to train on historical transitions, changes that you knew broke the system. You want to train on those, right? And then you want to test on historical transitions, break and fix. So again, a transition is just a break or a fix. If something can fix the functioning of a test, then the negation of that could easily break the functioning of a test. And you really want to find both when the test goes from pass to fail and also when the test goes from fail to pass, because the same sort of signals that you're looking for will be available in both of them. So this is kind of what we did. We did a study on this. I wrote a paper in 2018 with Claire on this. We'll talk about that in a second, for evaluating RTS. So what did we do? We used a data set of actual transitions from post-commit at Google. When we committed things that actually broke the test, right? We tested the RTS algorithms, like different algorithms, right? By setting a skip rate. So we prioritize all the tests using the AI. The AI says, this is the most important test to run on this change, and this is the least important test to run on this change, and everything in between, right? And then you start skipping tests. You skip tests in order of the priority that the AI has assigned, right? And you look to see, we know that test 5, right, was the one that caused the transition. It's the one that's going to break, because we can look at the data. We know from the past that when this change was submitted, it broke test 5. Okay, so you go along and you look at, you start skipping tests, and you hope you never skip test 5, that the AI has properly prioritized the testing so that one of the last tests that we'll skip is test 5, the one that we know is going to fail, right? So an optimal algorithm would skip the test that failed or that transitioned last in the priority, right? So it would skip all of the tests before it skipped test 5, because it knew that test 5 was going to break, right? That would be an optimal algorithm. A pessimal algorithm would skip test 5 first. It would totally get the priority wrong, and test 5 would be right at the beginning. It would skip test 5 first, right? So that's the best you can do, the optimal algorithm, right? The one that's omniscient and knows which tests are going to fail. And the worst you can do is you skip the test that is going to fail first, right? And any reasonable regression test algorithm would be somewhere in the middle. It wouldn't be as bad as skipping exactly the wrong test, and it wouldn't be as good as getting exactly the right thing. So we tested several simple AI algorithms to at prioritizing the test to see, using several features, what exactly the outcome was, right? And we compared the results against randomly skipping tests. So we just randomly sorted the tests in some random order, shuffled them, and then said, okay, start skipping from left to right. And we want any AI that we have for skipping tests or for prioritizing the tests to be better than random, right? That's kind of like, if you can just randomly skip tests, that's a lot simpler than an AI, easier to implement too, right? So that's that thing. So the features that we use for this simple study, pre-submit history. So decrease the priority on tests that were run prior to the change being committed. So if you ran test 5 on your pre-commit and it passed, then just lower its priority, because we're pretty sure it's not going to fail post-commit if it didn't fail pre-commit, right? So that kind of makes sense, right? The transition count. How many times had this particular test failed before? Just like, if it failed a lot of times before, then maybe it'll fail again, right? Affected count. How many different changes that have been submitted between the last change that you tested and this one? How many different changes could break this test? How many changes have come along that could say, hey, this test broke? So that's one. Author count. How many unique authors have edited this file? It turns out that we did an earlier study that showed that the number of authors that changed a file, different distinct authors who changed a file, was an indication that file was likely to cause a breakage, because many different people were editing it, which is kind of funny. It's kind of an interesting outcome, right? And then we tried something very simple, shared directories. So what this means is you look at the path, you explode the path into elements, right? Atoms, the first path, second, third, fourth, fifth, to the files, right? And how many shared path elements were between in the leading part were the same between the test and the function of the file that changed. So we'll see if there's some, if tests nearby a particular code change were more likely to discover a problem with that code change. And then we had 3 controls, right? Random, just randomly skip tests, right? Optimal, where we skip the test that actually transitioned last, and pessimal, where we skip the test that actually transitioned first. Okay, so those were the features that we tested with this AI, with this regression test selection algorithm, and so forth. And we wanted to graph how they did. So here, this is a dense graph. So let me go a little slow, and I'll try and explain it. I've already talked about it a little bit, right? So we have all of our different things from the previous slide, like all of the different features and the ways of drawing these lines, right? And across the bottom, we have the skip rate from 0 to 100. If you skip all the tests, you're never going to catch a problem, right? That just makes sense, right? The green line, the dark green line that's at the top, right, is the optimal algorithm. If you were omniscient and you knew that test 5 was going to fail, you wouldn't skip it until dead last. So you can see it just, the y-axis here is if you didn't skip any test that transitioned, right, it would be 100%. So if you didn't skip any test that caught a problem, then it was 100%. And if you skipped all the tests that would have caught a problem, it was at 0%. So as you can see, the green is perfect. That's the one that knows exactly the right order. The red is inverse of perfect, or pessimal, where you skip those tests first. So it drops to 0 very quickly, or drops close to 0 very quickly, right? And then all of our other feature sets are in the middle. So interestingly, the random is the solid yellow line that kind of goes through the middle. That's random. And as you can see, random is quite a bit better than pessimal, and in fact, even better than our shared directory AI. A shared directory appears to be anti-correlated, right? It's likely perhaps that developers catch problems in nearby tests, but they didn't think of maybe something that's a little farther away. It's quite interesting that was worse than random, right? So that's interesting. And then everything else was a little bit better than random. The best was actually the author count. Now, if we were going to do better at this, we might combine some of these features together and let the AI sort of pick and train it. And we might actually be able to do better than author count. We only did each of these individual features by themselves, right? So also affected count, how many changes had come in that had actually potentially broken this test, That was also a pretty good indication, just slightly worse than author count. And then the other four were kind of very close to random. Pre-submit history didn't help a whole lot. Prior transition count didn't help a whole lot. Those other things weren't actually good predictors of whether the test was going to transition, because they were just slightly better than random. So I think, if you're going to do an AI for regression test selection and you want to make sure it's working right, please read our paper, because I think this is kind of an important idea about how to evaluate the effectiveness of AI in the space, right? Anyway, so that's kind of that thing. I also wanted to stop briefly and talk a little bit about this huge problem that we have in continuous integration of flakiness, right? So I've kind of conceptually divided this into three areas, right? The first one is the money part, right? It's the part that when a test goes from passing to failing, you want to find exactly the change that broke it, and you want to tell the author of that change, hey, you broke the test, right? That's the first row, right? That's the money slide. That's why we do CI. Now the second row is the test is flaky sometimes. Notice change 13 and change 23 and change 19 ran multiple times and had a failing result and a passing result at those different things, right? So in this case, like, the test author is responsible to investigate it, to figure out why the test is flaky. Now, let me be clear. When we actually look at this, test flakiness is caused by the code under test. It's caused by the test itself. It's also caused by the infrastructure, all kinds of different reasons why a test can flake or can be unstable. And it doesn't mean necessarily that the test is bad. It could be a perfectly good test that's showing you a problem in your code that needs to be fixed, like a race condition or something like that. But in this case, the test author should investigate, because they're the ones most familiar with the test, who might actually be able to do something about it. And then the third one is infrastructure, right? Sometimes there are external things that prevent the test from running correctly, which are not owned by either the test author or the committer. So I classify anything that is not owned by the team that wrote the test or wrote the code, right? If it's nothing they can change in the code or the test that would eliminate this source of flakiness, then it's infrastructure to them. Could be a library that's provided. It could be the network of the computers that it's running on. It could be the computers themselves. There are all kinds of things that can cause this sort of infrastructure problem. And to the extent possible, we should try and automatically classify these items for infrastructure, let the infrastructure teams look at them. This was something we did at Google. It's something we did at VMware, both, trying to classify things automatically that route them to the infrastructure, rather than showing the developer that it failed because the network was unstable. That's not something they can do anything about in their code, right? So anyway, that's that guy. Now, this is a term of art, it's failure identification. A failure is detected when a pass to fail transition is observed. So in this case, one of the changes between change 13 and change 27 broke the test, and we detected that it broke. So any of the changes between change 13 and change 27 could have been the one that broke it, but all we can tell right now is that it is broken, right? And then the failure is identified when the list of changes is resolved to a single change. So you have to do something like regression identification. You try and find out which of those changes. You run the test at all those different changes, and you figure out which one of them starts the failure stream. In this case, change 23 broke the test. So that detection is when there's a failure that happened that's been submitted, and failure is identified when you have exactly one change that is the one that you can tell broke the test. So that's the idea of failure identification, right? And then for flakiness, if the test fails and passes with the same test and the same code, you can calculate a rate, which is the number of confirmed flaky failures over the total number of test executions. In our example, we have 3 flaky failures out of 11 executions, so we have a 27% flaky rate. It's a pretty flaky test, and one that probably should be investigated to see why it's so flaky. This is not a good signal about whether the software is broken because it's flaking quite frequently. So we definitely don't want to require action on each and every flaky result. At VMware, this produced a lot of toil, 12 times as much as if you just looked at the flakes after the fact. At VMware, we found that only about a third of the flaky bugs were fixed. So if you filed a bug due to a flaky test, only about 1/3 of the time did it actually get fixed. So they were kind of being ignored by everybody, right? And there was no prioritization signal, right? So a flake that happened 1 in a million times or even 1 in 1,000 times was treated the same way as a flake that happened every other time, right? So there's a big difference between a test that flakes 1 out of 2, like flipping a coin, and a test that flakes like 1 in a million times, excuse me, where it's very infrequently happening, right? So you want to act on the flakiness rate. You want to look at that flakiness rate. At Google, we automatically quarantined a test if it was more than 1% flaky, like if it failed more than 1 time in 100. And at VMware, we prioritize action based on the flaky rate. Our flaky rates are a little higher there. And fixing an infrequent flake, like a very low probability flake, might be diminishing returns. It could be really hard to fix, even if it's in production code, because it could be a rare thing that never happens or very infrequently happens based on timing or based on something else. So prioritizing based on the flaky rate seems a good way to sort of investigate and to help make the CI system work better, but also, if it's a real product issue, fix something that your customers could be experiencing as well. So that's that. So infrastructure, right? It's basically defined as a failure or inability to run a test caused by systems outside the test code or the code under test, right? It's something that that the team doesn't have any control over. The goal is to prevent investigation by the dev team because there's nothing they can do. They can't fix the test code. They can't fix the production code to avoid this flakiness, right? And you want to write code to automatically classify these, right, into infrastructure and focus the infrastructure team on the most prevalent ones across the entire system. What are the most important causes of test flakiness? So for example, at Google, we had WebDriver tests that were quite flaky and they often failed to provision a browser. So if you couldn't connect the browser to the web backend so that you could run the browser-based testing, it would produce a failure. And this was something, noise in the system, that we had the developers looking at. So we actually went in and spent a lot of work to categorize that automatically as an infrastructure problem, right? We went in and fixed the WebDriver, the way it reported these things, to say, no, this is really an infrastructure issue. It's really because we couldn't provision a browser. And then we would just automatically retry those and we wouldn't show them to the development team so that they didn't have to deal with this noise in the system. But we would count them and then send them to the WebDriver people to see if they could improve it, right? So that's kind of how that worked. Okay. Now talk a little bit, transition a little bit into continuous delivery, right? So what is continuous delivery? Really, you want to deliver as frequently as you possibly can. This reduces the risk per release. It increases the value stream going to your customers. It's kind of the best practice now in our industry. And as possible, varies by the type of delivery, right? So a backend microservice might be able to be pushed continuously, like Netflix pushes out every single change all the way out to their backends, right? Web front ends, maybe you change that a little less frequently because you want the front ends to be fairly stable. Mobile device applications, you can only push stuff through Amazon Store or Google Store or Apple Store at some rate. You can't send, in fact, Apple has, they have review requirements, so you can't push to them more than about once a week, right? So that just by necessity means that you can't push it as frequently as you can push your backends. And then sort of non-safety critical firmware and operating systems, right? You can't push a new device driver, operating system type thing as frequently because it takes longer to make sure that it's working properly. And then safety critical, like the anti-lock brakes in your car, that's not something you want to get frequent updates to. And it scares the crap out of me when my Tesla, gets an over-the-air update from Tesla Motors, because it can actually change the driving behavior of the car, right? So one of the interesting things, how many people have like an app like Facebook on their phone, right? So if you have Facebook on your phone, they want to be able to push new behaviors to you like instantaneously. They don't want to wait for the Play Store, the Apple Store. So essentially, applications on your phone have largely become just like the Facebook application in particular has become just a browser. It's a browser on your phone, and it's customized a little bit to Facebook, but there's very little behavior that's in there. Almost all of the behavior comes from the backends and can be changed instantaneously by Facebook, or Meta now, I guess, whenever they want to change it, right? So that's kind of a trend in the industry also, is to try and push more and more of the behavior up the stream of value so that you can release it frequently, change behaviors frequently, and try things out, right? That's kind of become the industry practice. So less and less behavior is going to get baked into apps or baked into your phone. It's more and more going to be coming from the backends and defining the behavior of how things work, right? So they can push it more frequently. So for continuous delivery, how do you do it? You need a mainline development model. You really need good automated testing with continuous integration, the stuff we talked about before. And then we need this best practice of A/B canaries with automatic evaluation and rollout. If you're going to push frequently, what you do is you push some backends, maybe they get mirrored traffic. You monitor them for signals of badness and goodness, try and make sure they're no worse than the current version, and then roll it out, or decide that it is worse than the current version and not roll it out. This is how Netflix pushes out almost every change for developer out to the web for their backends, is because they have all kinds of telemetry and signals, and they have ability to fork the feeds of people trying to watch movies and so forth. And they can tell pretty quickly whether a new version is working or not, and either continue the rollout or move it back. And then because you want to be chipping very, very frequently, you have to have feature flags so that code that isn't finished or features that aren't ready don't end up impacting users in bad ways, right? So this is how you have continuous delivery with features that take a long time to develop. Even if you're going to take 3 weeks or a month or 6 months to develop a feature, you feature flag it off, and most people can't see it or detect it or know that it's there. And then you work on the feature, and once it's ready, you turn on the feature flag, and it becomes available to your customers. So that's how you handle like long running features in a system where you're delivering continuously, right? So the canaries are really good for backend services, but you can also use them for almost anything. Like, so for example, Google releases a new Linux kernel every month using canaries and slow rollout to over 1 million servers, right? They take this operating system, which is key to their business, and they roll it out across all of their servers, 1 million of them once a month. And they continuously do it using this canary process. And as I mentioned a couple of times, Netflix pushes a canary for every single change to their back ends. And if you press play and it doesn't work sometimes, that could be because their canary isn't working. And it's a bad day, but it's not, nobody died, right? So it's okay. So the workflow is the service is deployed to a small sample of the traffic. You monitor for the key metrics, and you compare the current release to the new deployment, and you roll it out if the canary metrics say everything is good. You can fully automate that. You can get better and better at looking at which telemetry signals to look at to try and say, yeah, this canary is good or it's not good. I think Netflix has the best practice in this area, and they've only open sourced part of it with their open source canary tool. They don't do the A/B testing. They do just the slow rollout. So anyway, but it is a technique, and it's something that companies should be considering to release more frequently. So, and then this whole bit about feature and experiment flags, right? You deploy this feature in some dormant state. You enable the feature for a small number of users. You collect all the key metrics, and you roll it out to the users if the feature improves the metrics. So you constantly want to be testing new features with a small sampling of your customers. It's pretty easy to do that with these flags. Netflix has some very sophisticated ways of making A/B comparisons between different features, with it not on, and collecting telemetry on the sets of users who were using the new feature, the ones who weren't using the new feature, whether whether it's an actual improvement, whether you watched more or whatever, based on that stuff. So that's kind of how feature and experiment flags work to help, again, with features that take a long time, or with features that you want to try to see if you can get users to do something, to act in a certain way, maybe buy more of your product or watch more movies or whatever, right? So, okay, so that's kind of it. This is the recorded part. I'll be live there to answer your questions. But I really appreciate your time and attention today, and thank you so much.